Welcome to Tips and Tricks video. In this video, we will demonstrate how to use transform feature to perform transformation of field variables from one coordinate system to another coordinate system. We will show two examples. In the first example, we will demonstrate vector transformation utility. The second example deals with the matrix or tensor transformation. Let's look at the model of the electromagnetic motor with permanent magnets. We use magnetic fields, no currents, physics to solve the problem. Here we have a set of permanent magnets with radial and circumferential magnetization. We solve the problem for the one sector only and assume rotational symmetry conditions. The resulting magnetic field is shown in the slice plot, and here we use sector 3D dataset to visualize magnetic field over the full geometry. The magnetic field has X, Y, and Z components related to the global Cartesian coordinate system. But what if we want to look at the radial or circumferential components of the magnetic field? In other words, we want to evaluate components of the magnetic field in cylindrical coordinate system. Can we do this? The answer is yes, we can. This can be done using transform utility for variables. But first, we need to activate these utilities. We go to the Show More options and find section Variable Utilities, and then check this box and click OK. Before proceeding, we want to be sure that we do have cylindrical coordinate system. This coordinate system is defined under component definitions, cylindrical system 2. We will use this coordinate system to perform transformation of the magnetic field vector from global coordinate system to this local cylindrical coordinate system. Now we are ready to perform transformation. Under component node, right-click definitions and select variable utilities, and then select vector transform. Then proceed to settings window for vector transform. First, let's select all domains where transformation will be performed. Then we have to define input vector. Click Replace Expression, go to the magnetic fields, magnetic flux density, and double-click magnetic flux density. This is the field variable which will be used for transformation. Make sure that the global coordinate system is selected as input coordinate system, and then for the output coordinate system, change a default setting to the cylindrical system. This completes settings for the vector transform node. Now we can update solution and plot components of the magnetic vector field in cylindrical coordinate system. Let's go to the slice plot. To plot components of the vector field in cylindrical coordinate system, go to the Replace Expression, then Definitions, Vector Transform, Transform Vector, and then double-click component of the local field you want to visualize. Let's visualize radial component of the magnetic field. Double-click and click Plot. So this is the radial component of the magnetic field defined in cylindrical coordinate system. Similarly, we can plot circumferential component. We go to the component definitions, vector transform, transform vector, and double-click phi component of the transformed vector. Plot, and this is the plot of the circumferential component of the magnetic field. So far, we demonstrated how to evaluate components of the vector field in local coordinate system. But what if we have tensor fields, such as stress tensor or strain tensor? Can we do similar transformation for the tensor field? The answer is yes, we can. To see how it works, let's take a look at the example of the solid mechanics. Let's open new model file. Here we have solid domain, and we use solid mechanics to solve the problem. Bottom of the solid domain is fixed, and we applied axial displacement at the top of this solid domain. After problem is solved, we can take a look at the default plot for the stress. This is the mesostress. All components of the stress field are evaluated in the global X, Y, Z Cartesian coordinate system. Now, what if we want to evaluate hoop stress or radial stress? To do that, we have to create first cylindrical coordinate system. Go to the component definitions, right-click, coordinate system, and select cylindrical system. Next, add matrix transform node. To do that, go to the component definitions, variable utilities, and select matrix transform. And then go to the setting windows, select all domains, and then go to replace expression to select component of the tensor to be used for transformation. Click replace expression, solid mechanics, stress tensor, and select stress tensor spatial frame. Double click. This is the tensor component which will be used for transformation. We use global coordinate system for the input, and for the output we have to use cylindrical coordinate system. We have to use cylindrical coordinate system for the row transformations and for the columns of the tensor. And this completes the settings for the matrix transform. Next, we go to the study and click Update Solution. Then we go to the multi-plot group line graph, and here we have plot along the circumferential edge of the X component of the stress field. Next, we duplicate line graph 1, and now we want to plot hoop component of the stress field. We go to the replace expression, definitions, matrix transform matrix, and find hoop component, which is V phi component. Double click and plot. So the blue line is X component of the stress field. The green line is hoop component of the stress field. The hoop component is negative and constant because we have uniform tension. Similarly, we can visualize radial component of the stress. Duplicate line graph 2, go to the replace expression, definitions, matrix transform, transform matrix and find the expression for the radial component, which is VRR. Duplicate and plot, and the red line is radial component of the magnetic stress field. And radial component is 0, as it should be, because normal component of the free surface of the stress tensor is 0. That's all for now. We have demonstrated how to use variable utilities to transform components of the vector field or components of the tensor field from global coordinate system to user-defined local system. Hope this was helpful, and thank you.